Welcome to the AOML Science Seminar. Today we have Dr. Joe Cione who will be presenting some of his work.
Well, thank you for joining online or in person. Appreciate it. Dr. Joseph Cione is my name for those who don't know. And this is kind of cool. We used to do these informal research reports every year for many years. We kind of got out of that a little bit. And now if you think about a lot of the talks we do are typically 10 minutes, maybe 15 minutes, sometimes even 3 or 4 minutes, these lightning things we do. So it's kind of nice to have a longer one to get into a little bit more detail. And because of that extra time, I decided, I'm going to look at basically what I've done. Not everything, obviously, in 45 minutes, but looking back even before we started looking at some of these emerging technologies, the drones, some of the lightweight sondes, the modified sondes. But I want to go back to what I really started with, and that's the air-sea interface and looking at buoys. So when I first started working at HRD, I said, what do we have down at the air-sea interface? My background is in physical oceanography and meteorology, looking at extratropical cyclones, so not even tropical cyclones initially for my PhD. And it really turned out to be, what did we have? When I first started, even drop sondes weren't around, right at the beginning of drop sondes. So from a database standpoint, it was really buoys. So I started looking at fortuitous hits tropical cyclones had with these buoys. So I've done this for years. We put together a database. This was, Evan Colleen helped me with this. This is the TCBD Tropical Cyclone Buoy Database, updated through 07. It's still been updated through 2018 now, but these plots are from papers that we wrote in 2000, 2003, 13, even 2015. So you can see the location of the buoys. You can see the tracks too of the storms here. Red is for a filling system. Gray is kind of steady state, and green is intensifying. So, yeah, somebody, can you mute your mic there? We can hear kind of garbling, not even words. So this is a little bit different view. Again, we have probably twice the amount of data that I'm showing here now, but this is from, it gives you a radial look of what's going on in azimuth, so it's pretty well distributed. And this is interesting too, because if you look at some of the work Kerry Emanuel did in the 80s to say, assuming we have an isothermal inflow, so as air kind of spirals into the storm, that it's pretty much in equilibrium with the sea. And I was looking at these buoy data, I said, that's not even close. That's not even close to true. So there's a lot here, and I don't know if you can read the details, but I'm trying to get this, there we go. So if you look at this here, this is air temperature, and this is really the big one. So that you basically see that the ambient, this is radial distance from the storm. So we can see that when we're out here, this is sea surface temperature, the dot dashed above it. So we are, actually it's true. So you can see why that assumption was made, well out of the way where we have observations. The air, the tropical air mass, radial, well away from the storm, the ambient, is in equilibrium with the sea. But as you spiral in and you get sea spray, rain, etc., you get this cooling because you're not saturated. The air, the relative humidities of those parcels that even near the surface are about 80%. Bottom line is when you get into the inner core, you've dropped about 2 degrees. And what that does is increases your air-sea contrast. So this was, a lot of people know this now, especially with a lot of drop sondes we can see this, but back then this was a new finding. And these are just other plots, wind speed and pressure as you get closer. Of course, you would expect the pressure to go down. Okay, why is that not working?
Click back on the screen.
Oh.
Usually,
Okay. Yeah, I'm just going to use the arrows. I'm not going to use that anymore. So let me go ahead here. So another thing too that early on I started to see was you would see these. This is an ADHR sea surface temperature image after Hurricane George in '98. This is going back some time. But you could see this huge cooling, particularly to the right where the storm track was, and particularly to the right of it. And it was sort of not assumed. A lot of people said, well, you see this cold wake, we get 3, 4, 5 degrees C cooling. And as I just showed, that's really not the case at all. So you can see here the background SST, and if you're looking towards the western part of the Gulf of Mexico, is roughly about 30, maybe even a little higher than 30 degrees Celsius, whereas the post-storm environment is about 25 degrees or so. And that's a huge difference. So I started to look at, Eric Gilhar and I said, okay, we have this buoy data. Let's really concentrate on what is the SST cooling under the storm as the storm is there. So yikes, the preconceived idea of this giant amount of cooling just is not true. So this is a PDF looking at cumulative frequency for the change in SST defined as the ambient SST well away from the storm, and then within a radius of either 60 kilometers, which is the dark solid line, or expanded out to 200 kilometers. And as you can see, if you look at the 50% frequency line there, you're still talking on average, either of these curves, about a degree. That's what you see. You see about a degree cooling on average. Now, everyone likes to get into, well, what happens if the storm stalls? What happens if you up against a complex oceanographic situation? True, but look how infrequent that is. That's less than 10%. If you want to get a 3-degree cooling under a storm, well, what is that? 3% of the time? It's extremely rare. So this just kind of put bounds on what we should expect, and is sort of the boundary condition. This has been referred more than any other paper I've ever had, which is kind of crazy. And it's used a lot by coupled modelers to try to see what their models can represent in the core. And to this day, there's very little in-storm data to do this. So what about this? So I gave you the yikes for, you see the cold wake and, hey, what's actually happening for the data? Unfortunately, it's a while ago, so I'll cut, it's not trying to slam any models per se, but when we looked at what the air-sea interface was with the models, Eric and I, we compared that with the TCBD. Again, it was kind of yikesish. So this is for 2011, and then sort of composite for the year for the model, and also composite from the buoy database. So the blue is the buoy, and the red is from HWOR. So you got SST on the left, air temperature on the right, in the middle, sorry, and then 10-meter specific humidity on the far right. So you can see that there's not much cooling going on, but the middle one is probably the one that really jumped out to me. You have this warm bias at 10-meter air temperature for the models. Typically, you'll see 25 or so in the core. Very rarely will it ever go over 26 degrees. So it's about a 2-degree bias at this time. But what's interesting, on the bottom two panels are the del. So you have the del T, which is sea surface temperature minus the air temperature, and then the Q, del Q, is the specific humidity at 10 meters subtracted from the sea surface temperature Q, whatever the SST was. And the lesson learned here is, particularly on the right panel, which is del Q, is you get 2 wrong errors. Sometimes you subtract them, you get kind of close to the answer, the correct answer. So you can see that the red and the blue are overlapping. So right answer for sort of the wrong reasons. But this was good. We identified something in the model there, that there was this artificially capping the SST cooling that was really not known, or it was known, it was in there, but that was changed after this work. So I was glad to be able to do some sort of diagnostics. I won't spend a lot of time on this. This is, again, the top panels in blue are the buoy, and you could just see how the model for this year, for 2011, compared. You can see it's more constrained. The variability of the SST is less, and you can also see it's skewed to the right. There's a little bit of a bias, a warm bias. You can really see it with the air temperature. This is the same sort of plots. By the way, each one is from the left is closest to the storm, and as you go to the right, it's farther from the storm, so that's radially binned. But you can see that it's a different way to display what I just showed before, and same thing with Q. So it's going to take me a minute or two to explain this, but this is pretty interesting. So if you've got, we're going to concentrate on the specific humidity difference, where really is driving the enthalpy flux for hurricanes. So if you look at del Q, which is, again, Q10 minus the QSST, you have 2 things, right? So the atmosphere is responsible to some degree through convective processes. Of course, the ocean, it's not a linear process, because the ocean impacts the near surface environment as well. But the atmosphere typically responds on convective timescales, and the ocean largely, especially once everything is mixed, is operating on inertial scales. So I said, everyone will agree the del Q parameter is quite important. But what's driving it? Is it the changes in the Q? Is it changes in the atmospheric Q? Is it changes in the SST? Or is it, a combination half and half? So on the left panels, you'll see wind speeds between 20 and 25 meters per second. And then on the right panels, you have higher wind speeds, 30 to 50. There's not that much change between that, but the top to the bottom, which is buoy top, HWRF model version 3.2. I'm sure we're many versions past that at this point, but this is at the time what we used. So you can see in red is the atmosphere, so that's the Q10 relationship. So what basically we were plotted here is the del Q versus Q10 and Q SST. And the takeaway from this is that you probably can't read it, but the R squared explained variance from the buoy data is about 40 to 45% R squared. Whereas the ocean component of that ranges between 11 and 19%, so roughly half of that. So what that's saying is that the variability associated with del Q is largely driven, or certainly more driven, by the atmosphere. This is the crux of a 2015 paper I wrote. If you want to learn more about that, I talk more about that MWR paper. But if you look down below at what we saw for the equivalent for HWRF, it's almost exactly opposite. So here we see that the contribution from the ocean is roughly the same that we saw the contribution from the air with the data, with the buoy data. So it's 44%, you can't read it, ranging between 38 and 44% for the ocean explained variance, whereas the atmosphere component of it is between 8 and 20%. So it's less, so it's reversed. So I haven't looked at this more. Maybe this is something we can actually look at again with the model, with the current version model, but we're not getting that right. And I can tell you that's something that probably ultimately we want to do. So this is going to be, you can hear some music coming on, and I'll talk through this. It's about 3 minutes. It's good, so you can watch and I'll talk through it. So at this point, now we're about 2005. So I had halfway through my buoy stuff. I continued to do it, well through this. This is 2005, working with NASA and Aerosonde Corporation, which is a Australian group. And basically, we got some hours to use this drone. And it wasn't built specifically for hurricanes, but we said, you know what, we're going to try to do this. And we started working on this maybe 03 or 04. And then we finally got a chance to do something that, even with all the crazy stuff we've done with drones, this is probably still the craziest thing, at least from my career, we've ever done. You can see how this thing launches. It's not dropped from a P3, it's land launch. It has the capacity to go about 24 hours. It's a gas-powered engine. It's about 20, I can't remember exactly, it's been so long, about 25 pounds, I want to say, about a 6-foot wingspan. And that's literally the launch going into Ophelia. This is the first time a drone on planet Earth that has gone into a tropical cyclone. So we need to get that in the Guinness Book of World Records. But this particular flight was 18 and a half hours. And we took off from Wallops Island. You'll see we actually had some reconnaissance flights too. They show a screenshot of us flying in there. Air Force was there too, as well as our P3s. So this is, there you go. So this is really what I started concentrating on, because I knew we had kind of pushed it. So it's still trying to get that low air, low surface layer, boundary layer structure. This was more about the technical capability of doing it. The data itself was not that great, honestly, because it wasn't built to fly 18 hours over the ocean. We had some issues with the relative humidity freezing up and salt incrustation, we think. We don't know. We actually got the sensors back, so we looked at them, but there was a lot of unknowns in that. But this was more of a concept to show that we can do it. And we did this again in 2007. And 2005, 6, 7, 8, we had campaigns, but we had to set it up so we would operate from a certain place. We operated from Key West, from in this case, we operated from Wallops a couple of times. We tried to go out to Barbados. The concept of operations was just too difficult. We only tried twice and were successful twice. So we're 2 out of 2. But the unsaid part of that is we set up about 10 times and we only had two opportunities to do it. So towards the end of this sort of campaign to use this technology, I started realizing that this isn't really the way to go. And I saw Tony Brushes was listening to this call, which is great, because he met and that kind of changed everything. And he said, we fly P3s in the Navy. This is actually coming back from Ophelia, by the way. This isn't some test flight. It's literally coming back from the hurricane. I don't think, no, I actually know it's not true. We have a model here in AOML, but it's not that plane. I still want that plane. It exists somewhere. We ought to find that. So Tony basically said, listen, you want to do, here we go. Do you want to do any sort of follow-up using the P3s to do air deployed? Long story short, in 2009, we did a test, and we didn't have any money though. It was great, it worked, there was no payload. We dropped out of the P3, so we basically shelved it. That was 2009. This is Hurricane Sandy, and it caused a tremendous amount of devastation to New York and the whole New England region, lots of flooding. And it was devastating for sure. These are a couple images I pulled from the net to show that how much New York's not exactly set up for this sort of thing. The infrastructure's over a century old. But sometimes you get the phoenix coming from the ashes, and this is a good example of that, because after this occurred, Congress put a good chunk of money towards hurricane research, and we had shelved the idea of this air deployed drone. And we had an opportunity to get some funding to do it. Not a lot, but we had about 5 actual birds that we're able to get and test. So we essentially got a new concept of operations, small uncrewed aircraft systems, which is going strong today. We leverage what we have, right? So I tested the old ConOp. We learned what we can do. And this new one is much better for many reasons. We can use what we have. We use the P3 as a really sophisticated bus to get us there, and we still get to observe this critical region of the storm where we can't really observe too long. And we concentrate our observations instead of ingress and egress. Remember that 18 hours I said? Well, 15 of those hours were getting there and coming back. 16 actually. So we had 2 hours on station at most. This way you can really concentrate and just have almost all of your observations where you want them. So the goal is to really improve our understanding always first. Operational situational awareness, fancy way of saying get this data to the operational forecast as quickly as possible. Through that improved understanding, get better models, improve the physics. Jun's sitting here next to me. He's used this data and is using this data to improve the boundary layer physics of the models. And then ultimately, we believe that will improve our intensity and maybe even small short-term track forecast performance. What can we use these things for? I'll just show you how they work physically in a second here. But basically, it's sky's the limit. We can use them for eye wall modules. We drop in the center of the storm, and that's our primary one. And then we spiral out into the surrounding eye wall. We can do inflow modules, meaning we start out well away from the storm and kind of spiral in, use the way Mother Nature gets the air into the storm. We kind of copy that. And now with the longer duration drones that we have, we can do center fixes. We can actually hang out in the storm and follow along, or do these penetrations in and out of the eye wall, which I know Sim and I share an interest in, and looking at some of these mesovortices and also looking at the momentum and heat flux and moisture flux exchanges that we have horizontally across that very dynamic interface, the eye wall and the eye. So this is what it looks like. This is Coyote. So this is sort of version 1 of what, let's call it version 2, because version 1 was the Aerosonde. So version 2.0, I guess. This is how we launch them out of the AXBT chute, CLTs. And this is sort of a cartoon of what it looks like. This is still, again, valid for the Coyote that we flew, but it's still valid the same sort of way we do this, except minus not everyone uses a parachute. But we transmit the data through RF, and we've been going since. So with the Coyote, we basically had about 20 nautical mile range, less than an hour. So it was, again, sort of feeling our way to a new ConOp of how it worked. Very good data. In fact, we were able to publish from 2 storms that we flew into Hurricane Maria in 2017, and then we had 1 flight using this drone in 2018 into Michael. And no, this is not a real shot. I wish, but there's no, I don't know though, how would you actually get this picture? You gotta think about that too, right? So if you haven't seen this paper, look it up. It's in BAMS 2020. Lots of people on this, very collaborative work. Some of the highlights from it, we had 7 drops. 6 of them were in 2017 in Maria after it made landfall and continued on from Puerto Rico. The devastating effects were there. This is basically over the open ocean. And then we had 1 drop in Hurricane Michael as the storm was intensifying before it made landfall as a category 4 or 5. Is it a 5? I'm not sure. It did go as a 5? Okay, so we saw that. That was interesting and as it was intensifying. So it's hard to capture intensification. It's a pretty rare event, but that was interesting. We got that. So just to give you an idea what it looks like. So this is a lower fuselage radar, and you can see in white what the Coyote did. This is Coyote drop 1. Jun Zhang and others, and Josh Wadler and a few others, we're looking at that particular drop. It's got very low. I'll show you a little video of it at the end where we think we got the surface layer, so we can potentially look at flux issues and other turbulent structures. We're going to try to publish a paper, offshoot paper from that. The second one is maybe it's hard to see. It's not. You can see that white line. This was an attempt at a. This was an attempt at the an inflow module. Didn't last as long as we had hoped, but this theoretically should have been able to get into the eyewall region. And this is really what all 7 flights. So we have altitude on the left and time on the right. You can see those 2 on the extreme left there. Those were essentially expensive drop-ons. They did not deploy. But they still are of use because we got 10 hertz winds as we were coming in, and they were also right at the eyewall boundary. So we could kind of glide them in. But the other flights, you could see how we did step descents as we came in, and that flight 1 on the far right is the one I was talking about. We got to about 140 meters or so before they ultimately expired into the ocean. So this is just a flight number 7. This was the last flight we did into Michael, and you could see the wind speeds we got were at the time were a record at 82 meters per second. Maximum wind speed in the eyewall at close to about 2,000 feet, a little over 600 meters. That record held for 4 years, but we broke it in Ian, which I'll get to later. But you could see also that we also were able to capture vertical wind speeds, which were pretty violent towards the end of that flight when we got those max winds, and we saw vertical wind speeds between minus 10 and plus 10 meters per second. And we also have the radial wind there captured. This is some work Altu actually led, and we have a paper out of as well, showing the importance of the data. I kind of wish we had done 0. This is 0 to 2 kilometers. If we had done 0 to 1 kilometer, it would have been on the left is the kinematic observations we have. It's drops on Coyote, SFMR, et cetera. And on the right is the thermodynamic. But if we did 0 to 1 kilometer, it would have just basically been all the Coyote, a couple of drops ons we had. But it's very valuable to get this data because there's really, it's not in addition to, it's really that or nothing. This is work also from that 2020 BAMS paper to show that we can kind of diagnose the model. So Evan Kalina led this work where we basically flew the Coyote through the initial period, the initial fields of HWRF. And you could see in these cases, so the top 2 panels are the initial fields, and then it's a 72-hour forecast at the bottom. You could see that HWRF was cooler and drier, which is interesting because you remember this is 2017. It was warmer and more moist, relatively speaking. So over that 6-year period, we kind of flopped. And of course, this is only one storm to see if this is consistent. But this is a nice tool to use to see how the model is performing. And I would like to do more of this, especially as we get routine observations. This is part of Altu's work too. This is to show that structure can be changed from using this platform too. So on the left side, it's without UAS. This is the wind speed at 10 meters. And then the middle panel is with it. and then the difference field on the right. So you can see that we really sort of brought in the asymmetry that was not really captured as well without the UAS data. And again, remember, this is essentially less than an hour. These are two drones that we had about, if you combine them, about an hour and a half, about 40 minutes each. So that's not a lot of data, but it's in the right place, and it's where we don't have much else. So it can make a significant impact. And also, I don't have it here, it also impacted the track. You can really kind of center where the storm is on short timescales. And before landfall, that can be significant. We really didn't think about looking at track much before. So a lot of people say, you're gonna get a camera on here, and you're gonna get a camera. So I keep asking that. So this isn't a camera, but this is the telemetry video. So every second here, it's sped up to 6:1. So it's not this quick, but you can imagine that the horizon is the ocean there. The brown's the ocean, the sky is blue. And what you can see here is that the one that looks like the P3 is actually the drone, and the person with the red, the circle there is actually the P3. And we had to do this song and dance for the Coyote. One of the reasons we stopped using the Coyote is we had to stay within 20 kilometers. So we had all these very complex mission parameters to stay close, and the pilots did a fantastic job. This is flight one, the one we got very, very low. So you can't probably see it, but right now we're 470 feet off the ground. But this thing can, and it's getting rocked around, obviously, but it stays afloat. In fact, at one point it does a 360, stays in the air after that for a little bit, and then goes in. So this was a learning experience too, to say, can this fly? Can this work? And the answer is yeah, it did, and it did pretty well. So there are things that we want to improve though, and that's a good segue. So that was 2018 was the last time we flew, and then we had to, I put in through the NOAA's SBIR process, I said, hey, let's get something that's not a military holdover, that really is exactly what we want, tell them what the requirements are, and let private sector come to us, right? And this is one of the three that we had. So we had 3 aircraft that came through. This was actually a military. This is Area I, the group that is responsible for putting the UAS into Hurricane Ian, which I'm going to talk about. But bottom line is, this is another example of using what we have, leveraging. We leveraged the SBIR program to give us companies that are very interested in flying with us. They told us, I put this out, they said, oh, no one's going to say they're not going to be able to hit your metrics or whatever you want. We had more companies come back. We had 17 companies that wanted to work with us, and we picked the top 2, and it's worked out really well. So this is recent observations from Hurricane Ian, which a lot of people should know and remember. It impacted the southwest shoreline of Florida, and it did significant damage. We flew right before landfall, and this is a team that flew. You can see everyone there. You probably notice a lot of faces there. I see Rob, and we also have the contractors there from Area I. So this is what it looks like. It's a lot longer, the 9-foot wingspan. It has a stubby mode, which is half that wingspan, and actually we did fly in stubby mode, so we've actually never flown in this fully configured mode. It was a technical issue why we didn't do that, but in the end it probably was smart. With that amount of turbulence, we might not have done this well with this extra long wingspan. It's about 27 pounds, so roughly the size of the Aerosonde. It's about twice the weight of what the Coyote was, but this thing can fly between 3 and 4 hours, which is much longer than we've ever had the capability. We've done a lot of testing. So yeah, I won't spend time on this. 3 to 4 hours, 55 cruise knot with the cruise speed, which is about roughly all of them fly about that, 27 pounds. We have about a pound of payload if we want to use it. So we plan on putting a camera on this eventually, probably not in 23, but it's soon, maybe as early as 24. So this was right in the middle of pandemic. Kudos to AOC and the pilot for pulling this off. This was January of 21, when it was near impossible to do anything. And we flew out of Pass River. The Navy allowed us to fly there. And this is slow motion, obviously. You can see there's no parachute, unlike the Coyote. This thing came out and flew really well. We got 190 nautical mile range to communicate, because we don't want the P3 to babysit. This was a huge success. And that's why we were ready to go into a storm. So we did, by the end of 21, we were confident that we were going to do it. So here it is. We had an earlier opportunity to fly. think it was in Earl. We didn't get a chance, and at the time I was upset, but that we didn't get to do that. But it turned out that this was a much better opportunity for us. So sometimes you gotta really, you never know what Mother Nature's going to throw you. So this is a composite loop, and you can see as it was coming off Cuba that you can see there was a, I don't know if I can do that again. Maybe I'll do it one more time. Okay. So you notice that it had a double eyewall, and eyewall, and went through an eyewall replacement process very quickly, cycle. And really, we're kind of surprised that it intensified the way it did. So you can see that structure, and it collapses down, and you got that wobble coming out at the end. And we were flying right about now, and it was a very, very rough ride. So I'll get into that. How rough was it? Well, before I get into that, where were we operating? We were operating, again, kudos to AOC for being able to operate under very trying conditions. They got family and friends that are in the Tampa area and Lakeland area. And we couldn't operate. Obviously, you just saw that loop. There's no way we're going to operate there. So we relocated to Houston and flew from there. And this was the plan. So it always looks good when you're planning something. All these great plans to do this. We were going to drop 39 dropsons. We were going to have the Flames module that was part of the TCRI program. Lots of things we were going to do. Isn't it awesome? And then no, we couldn't do it, hardly any of that, because it was pretty brutal. It was a brutal ride. This leg here, so we're coming in from Texas, this leg here, which was, we'll call it a west-east, but it's more like a northwest to southeast leg, was very, very turbulent. And we ended up going into the center of the storm. And thanks to the AOC staff again, we ended up doing a launch in the eye with the drone. And then this next bit here is getting out of there, because we were concerned. We wanted to make sure that the plane was okay structurally. So you can see we got out, and then these loops here is basically going through to make sure we were okay. The interesting thing is that this was a test of the range. Remember I told you 190 nautical miles in clear air. Well, we weren't planning on doing 135 right out of the box in a major storm, but we kind of had to. And it came through with flying colors, and it worked. This last loop here is we decided, you know what? We got to get close. We want to get closer. So this is our attempt to get close. And then at this point, we had about 2 hours of flight, 1.7 hours of flight with the drone, and it had run out. We were done, but we were getting ready to do a penetration. So Rob and I looked at each other. We were talking about it and said we were getting ready to do a run in after that. People were very nervous about it. And then the UAS expired into the water, and I was like, I'm good. And Rob made the call to say, yeah, we're good. We're out of here. So we never went back in again. So what it looked like is I think this is 15-meter resolution visible imagery. You can see the scalloping here on the southwest portion where we came through, and all sorts of interesting, in quotes, structures in the eye itself. Low-level mesovortex looking like structures. And we definitely went through the roughest part of the storm. So what did it look like? This is basically what we had for that leg, and we're looking at vertical velocities here ranging between mostly updrafts, the strongest updrafts. We had some -5 downdrafts, but if you're looking, the delta is about 20 meters per second over a very short amount of time, within less than a minute at some points. So for those not as familiar with aircraft stuff, so this is the pitch angle. So when the plane's going up and down, I'll leave it to the people who have flown more than me. I've flown quite a bit, but as far as exactly where this ranks, I can't say. But in this case, you can see that the pitch, delta pitch we're looking at about in a not quite 10 degrees, but maybe 6-8 degrees. Well, actually more than that, probably close to about 8 degrees maximum. So that's not trivial at all. And you can ignore, this is now the roll, so we're going sort of left and right. The far where it says 16 on, that's actually us in the eye, so you can ignore that. That's not part of it. But everything left of 16 minutes is real. And you can see that, this is pretty significant too. Got down to about -15 roll angle, whereas it was a +5 angle, not too much less than a minute before that. So that's about 20, more than 20 degrees in about a minute. So that's pretty severe too. But the thing that freaked most people out was this. So we don't, and I can say I really haven't experienced much of this. This is a yaw angle change. So you're kind of going sideways. And this is what dislodges lots of stuff from, inside the plane and where things really start to go flying more than some of the other parameters, I would say. And this, if you're looking at it, is about a 10-degree yaw angle change in a very short amount of time. And a lot of white faces after that. So this is just another, I think Jin, you did this one, right? You gave me this plot. So this is in the middle there, you can see height and time. So as we came in, we were at high altitude. You can see, and it's also wind speed. So high altitude, low winds in blue. And then as we got lower, you got the warmer colors there, reds. That's where we had our maximum winds, which were measured at 187 knots or 215 miles an hour, which blew out the other record that we had from Michael, which was 83 meters per second, and this was 96 meters per second. So it's pretty remarkable. And you can see the pattern that we flew. So we went into that southwest high wall, and we came in, we looped in. This is just another way to show the data. So this is the altitude with wind speed, and we spent a lot of time at 3,000 feet, as you can see. This is where you can see where we had our max observations, which are just above 2,000 feet, that 87 meter per second wind we had in the southwest high wall. This is interesting too, and our team has not, we just getting done quality controlling a lot of the data. There was some issues with it that are natural to go through it, but we have measurements that are over 120 knots here, and we're at 500 feet. So, this is some pretty interesting data, and even this data, which we're at 100 feet or so, we're still at 50, 55 knots. So this would be interesting. We're going to do a better job next time of really trying to calibrate where we want to go and how we want to do it. But this is pretty remarkable data that we're in the process of hopefully publishing soon. Just another way to look at it. So air temperature, so time series on x-axis, and we've got values. So air temperature, relative humidity, pressure, wind speed, altitude. So you can see altitude as we're going down, pressure's going up. These are these spike areas when we were in the eye wall, and we were able to do a correction for relative humidity too. So that data is actually going to be looking pretty good too. So we're interested in looking at things like enthalpy flux and momentum flux as well. This is just to show, and this is something we'll actually share with AOC too, is that we really didn't lose communication with this aircraft, and it's really impressive. So this is the distance from the P3 out to 130 nautical miles. And this is the connectivity telemetry loss. And you can see that only 3 times did we lose, and really at the extreme distances, did we lose communication with the P3 for more than 30 seconds. And if you actually go at, say, 125 or 120 nautical miles, we never did. The longest we lost was 20 seconds, and that was only a couple of times. So this is really good news, because this means we can safely, don't have to babysit this thing, and it can do its own thing. So with that knowledge, and this is the first time, we weren't sure it's going to go, and we could go farther. That's as far as the P3 was. Maybe we can go even farther, 140, 150, who knows? But even as long as we can, the goal is to make sure we can get the 110 nautical mile legs. And I think we did a good job of that. Getting towards the end here. So this is, for those who know what HD obs are, I'll draw your attention here to the wind speed. So basically 30-second averages, and it's not, that 183 knots was over a 30-second average, and it really stayed pretty strong here for about 3 minutes or so. So you can see ranging between 160 and 183 knots for 3 minutes time while it was flying through there. So pretty impressive. This data was sent to the Hurricane Center in real time. EMC had access to it as well if they wanted to do something with it. We're going to work with Mark DeMaria over this year to try to really improve upon that. So, in summary, we basically set a lot of records here: wind speed, endurance, distance from the P3. Really, and this is the future. Whether it's specifically this platform and other platforms, which I'll talk about here in a second, that's really not the point. The point is that I think that this sort of concept of operation has proven itself. And we think that, certainly the Altius is part of the mix for what we want to do going forward, and we're excited about that in 23 and beyond. So what is next? So we're post-processing the data. We're seeing maybe what sort of impacts, model impacts we can see, in boundary layer improvements, parameterizations. We're going to be adding a turbulence probe, which is really key to this year. We're doing some wind tunnel testing next month, Black Swift as well, which I'll get into here. It's another drone we're working on. And really just keep learning, right? Keep incorporating the lessons learned. It's like you learn a lesson. If you don't listen to the lesson, then why, then you're not helping. So that's my goal, is to always try to take a step forward. So I'd be remiss here if I didn't talk at least a couple of minutes here for the NEOTAC, which is a group. If you're not familiar with it, contact me offline. I've been doing this, it's amazing now, since the middle of the pandemic. We started in August of 2020. And so it's 2.5 years. And we bring together civilian, federal civilian, DoD partners, academic institutions, private sector collaborators to say, hey, show us your NEOTAC, particularly as it relates to hurricane sampling. Although, we're a little open on that. It can have other applications too. So there's over 60 talks. If you're interested in what we've looked at, as I said, contact me. But, the point of this is to keep learning, to keep getting what's new, what's next, what are we going to do? So here's some shots here. You can see the sail drone. There's a high altitude drone that stays in the stratosphere, can kind of stay up for a couple of weeks. It's interesting. We have dropsondes that are modified with sea surface temperature that work with AOC and NCAR to develop, and many other things, and also Skyfora, which I'll mention here too. So these really, what we want to do is take the best of this and have some field testing with it. Say, hey, what works? So what's up next? Well, with what is going to work, or hopefully will work, is now we're going to test this second drone, which is called the S0. Black Swift out in Boulder builds it. It's much smaller. It's about, with the other, Coyote was about 15 pounds, and the Altius is about 27 pounds, and this is about 3 pounds. So it's an order of magnitude lighter than the Altius. It has a built-in turbulence measurement. It has an SST measurement. I should have said that. So the Altius has a ability to measure sea surface temperature. This also has a laser, which the Altius does not. So maybe give us some information on the wave structure. It'll also give us better height assignment. That is going to be tested clear air in March. And we also hope to test it, if that goes well, in hurricanes this year. It's not out of the question. So Skyfora here, we have Kim has joined us from Skyfora. He's in the audience here, and we're going to do more balloon tests to test the sensors and compare them to the Vizsla sensors. These are really revolutionary. They're 1/2 ounce, just to give you an idea. So it's 15 grams. The non-mini dropson was about 1 pound. So this is about 3% of that weight. I'm not exactly sure what the weight, I'm sure other people know the mini sonde is, but I'm pretty sure it's still not a half an ounce. So these can stay up. The batteries, I'll let Kim answer some of the questions if they come specific to this. But as I said, 1/2 ounce. We're going to be testing this using the P3 this March as well. We have 3 versions. It's free, fast, and furious. So, and I didn't make those up, and I'm a car guy. I'm surprised I didn't make that one up. But the free is the 15 gram kind of float around, and they fall about the half the fall speed of a dropson. The fast is going to try to mimic a dropson. We'll put some weight to it. And then the furious is just going to try to give us a vertical profile. So we're going to test all 3 of these. I have some seed money to do that. And then we'll see where that goes, and potentially can try to test that as early as this year in hurricanes. We'll see. We did some sounding. So you say, well, how did it work? How do these sensors look? So the blue is Skyfora, right? Okay, the blue is Skyfora. You can't really see details. It's reversed too. So we're, as meteorologists, we're looking. So the top, the 1,000 is the surface is at the top, and then so it's reversed. The new plots will make sure the bottom is the lower part of the atmosphere. So where we care is this is temperature, relative humidity, and wind speed. So the blue and the orange are the comparisons between the Vizsla. And generally, it's good. We can have Kim answer a couple questions. I think it's a very good first start, and then we're going to be doing more drops later this week as well. And this is the second one. So that's it. Questions? Any sort of thing you want me to answer, including where is this picture taken? But I'll leave that to you. And some people should know.
So thank you, Dr. Cione. Let's go ahead and take any questions. If you are welcome to, you're welcome to write your question on the chat or raise your hand. We'll start with the folks in the room, and I will turn on the camera so folks can see you in the room. We have about 74, 75 people online. All right, Rob, go ahead.
Yeah, Joe, you mentioned for LTS, one of the last bullet points is you want to incorporate lessons learned.
Mhm.
What are some of those lessons, would you say, at this point, looking at the data?
Yeah, I would say, so we need to get automated, okay? And the thing is, we have this path forward, and I think we needed to be able to walk before we could run, maybe even crawl. I think we're past crawling with that platform. So I think this was a really good walk. So I think the lesson is we're on track, and it's sort of a confirmation of that. But there are certain things that needed to be shown and proven. But one of the lessons learned is let's not be overly concerned now that this thing can't tell us where it is. That's a key thing. So that one where I was showing the telemetry is to say, this year now we have deconflict with the Air Force as well. Let's let this thing do its thing. And I think it frees up the P3 to pretty much do what it wants now. So before this flight, I would have been like, I don't know about that. So that's one thing. Second thing is we flew in stubby mode. That was a glitch that was really fixable. Really should never have happened. Now we caught that. That's never going to happen again.
Will that increase the range or something? If you go
to It should. We should go to 4 hours, 3 to 4 hours. 4 hours is, I think we're going to get close to 4 hours, but contractors are being conservative. They're saying 3 hours, but we should get a lot more than that. So that was something that was fixable, and we didn't know. Also testing. Oh, one other thing from the RH sensor. When we launch them for the dropsonde, we condition it, right? There's a conditioning that goes, I think that has to be done, some software. These things sit in the drone for a long time. That conditioning routine was not employed initially. So we need to make sure that works so that we get the thermodynamic data we got. But a lot of little things.
All right, thank you. There's a question from Molly asking, where was this picture taken that we're showing on the screen?
Okay, so I'm going to ask Molly, can you hear me? I mean, can you talk? You're unmuted. So I'm going to ask you a year. Where are we physically? Take a guess. What time of year? And yeah, that's good. Let's just go those two. You have any idea? All right.
Right there, Nova Scotia.
So this is winter. This is offshore North Carolina during the Gale experiment. You have what they call a cold air outbreak, really strong cold advection. And you get these steam devils that come up, and it's massive amount of latent heat flux going on right now. Actually, probably a little bit less now because the winds maybe have calmed down. But this is, during the Gale experiment, 1986, sometime in February or March. I think some people, Bob Black actually told me Frank flew on these flights. Very bumpy, very not fun. You fly low in the boundary layer. What?
We flew through a bar spot, one of those situations.
I don't doubt it. So this is also a throwback to what I did earlier in my career before I did hurricanes, where we're looking at air-sea interfaces and boundary layers in these extremely turbulent, high enthalpy flux regions.
You really like boundary lows form over cold air outbreak. A lot of boundary.
Oh yeah, cloud streets, what they call it. If you look at it from the satellite, you can see it. I had one that was it was a blizzard from this. It was incredible. Cloud streets going from the south to the north because they still just couldn't really acclimate, even though they were over the ocean for many hours.
Couple comments here on your picture from Rick Lumpkin saying that he's seen this sailing out in Woods Hole in February during the gale, during climb mode.
Yeah.
There was a comment earlier about the weight of the mini sonde, and that was 167 grams. Thank you for that. And Chris Lancy has a question. Hopefully he can unmute and ask your question, Chris.
Okay, can you hear me?
Yes, we can. Go ahead.
So the question, Joe, thanks for the seminar. Really interesting to go back historical perspective. Those mini drop signs, you mentioned they float. Is it possible they could continue to transmit surface pressures while they're being moved around by the waves? I'm just envisioning having 10 or 20 or 30 of these giving pressure measurements well after they're launched. Is that possible?
Yeah. So I really didn't get into that, and thank you for bringing that up. Yeah, it's, not only are they light, and they measure obviously pressure, temperature, winds, and humidity. They believe, the manufacturer believes that the winds are going to be more accurate. But what's very interesting too is that they should float and give us sea surface temperature and pressure. So you can integrate, once you have these surface pressures, we can monitor it maybe from a RI standpoint, but also you can integrate up, and that should allow us to get better height assignment for the atmospheric, for where the winds are. Right now, we can't really do that with the Vizsla product. So yeah, I don't know, Kim, do you think, how long could they float around in crazy winds and waves like this?
Well, we could implement sort of a beacon mode that it transmits once in a while, not continuously, then it can live on for quite a while.
Okay, so we can go into a beacon mode and kind of conserve the battery. Obviously, it's electronics, salt and water and electronics don't go great. So it will fail at some point, but even just getting, some data, and these are lighter, so we were able to drop maybe more, we're going to drop more of them. So yeah, you could pepper them and they could end up landing in different parts of the storm. So it's very exciting. One last thing on that though, our balloon tests. I know we're talking about drop zones, but when the balloon pops, the Vizsla balloon pops, that's it. These experiments we're doing, you get a sounding on the way down too. So which is pretty neat also. And if that ends up landing in the water and you can get an angle to look at it, that could be sitting and you could actually be transmitting data back from the balloons as well. So very interesting stuff.
We have a question in the room, and then I'm going to go back to the online folks. Go ahead, Bob.
Joe, what's the range that you have to be from these drop zones or whatever you're using?
Great question. So I made sure that the drones and any sort of thing like this has basically AVAPs compatible. Not that you're using AVAPs, but using the receiver. So it's using 403 megahertz. So it has long range. So it should have very similar range that the drop zones have, and also, as I showed, the 190 nautical mile for the drones as well. So we're using the downside of using that is that you really can't transmit very fat data. Really, it's just going to be the bandwidth is going to be limited. But for what we do is really not that. You're looking at ASCII data that can be done that way. So it works.
Thank you. There's a question here about, it says, presumably the UAVs pass through clouds. Why is the RH almost greater than 80%?
Yeah, so we had a correction. So the 80% that you see really is 100%. So those it was actually 79%. It maxed out at 79%. It was due to, as I mentioned with Rob, that there was a routine that was not run, but they were able to correct for that. And we believe that compared to other observations we have from drop zones, that we were able to correct for that. So the 79, 80% maximum we had was really 100%. So I'm not sure if I answered your question on that, but we did have to do a correction with the RH.
I'll take one additional question online and then one in the room as well. A question regarding deployment of any products operationally for the 2023 season.
Yeah, well, we're still in this transition mode, right? So I'm working towards, to me, operational is buy a batch of these things and AOC knows how to use it. That includes training. It includes having enough flights that we know what it can do. We're not at the operational mode. So my goal for operational mode, true operational mode, is at least the next 2 seasons we're going to be in this mode where we're dropping as many as we can, 23 and 24. And maybe by 25, we can hopefully get to the point where we truly transition this to the weather service and or AOC. And we do have a signed transition plan. It's always the money though that I don't see any signed dollar bills yet. But once we are able to do that, so I think the next 2 years. So I can tell you, I have at least 16 UAS, the smaller version, the Black Swift. Actually, we used 2, so 14, and then we have 6 4-hour Altiuses on board. But I'm hoping to get more. We're going to be putting in there's going to be another call here soon, and we're going to go for a lot more UAS soon. As far as the mini sondes, the Skyfora sondes, we have orders in for at least 150 of these things coming in. And I have another batch of money so I can get more of those. So we definitely have, over the next 2 years, some resources to go to keep testing this.
Sujin, did you have a question? Go ahead.
The first thing is you have the intro slides. Can you do the similar analysis about the hubs, the current hubs they're going to put into operation in this season?
I'd love to. Yeah, I don't have it, but we could definitely do it. We could mirror what we did, kind of mimic what we did to see how it's changed. Yeah. I'm not going to be the one that's looking at the model data, but if someone wants to do it, sure, we can absolutely do that. Okay.
So get an intern. Let's find an opportunity to do this analysis. And second thing is is that possible go to high altitude?
Can you repeat his question?
Please repeat.
Okay, so Sujin asked, the first question was, hey, those plots you showed of the comparisons with HWARP, can we do with HAFs? And absolutely. So I'd like to do that. And I'd like to, because that's one of the reasons we're doing this, is to try to identify and remove biases and other issues that otherwise wouldn't be there. So 100% interested in doing that, especially in a couple modeling system like this. Second question was?
You showed the sUAS.
Mm-hmm.
So those system can, even though now you're limited by P3's altitude, but can you go like different platform to jump?
Can
we fly high? Well, remember now, we got the data void region. P3 is flying up at 10,000, and we have radar down to about a kilometer or so, and we don't have really low. So that's the purpose of this, is to go low. So it's not really the best use to try to go higher. Second issue is if we go above the melting layer, there's icing issues. So it's not really the best thing to do. Now we do drop at about, we drop from the P3, 10,000 feet. So we do sample a little bit as we come down, and we could spend time at say 5,000 feet if we wanted to for a specific purpose, but we're not going to really climb because that's not energy. It's not a good use of energy. So really any profiling we do is coming down. Now, I will say though, big thinking here, with Skyfora's half-ounce sondes, something I would like to do is maybe spend more time aloft, higher, and drop these things because they're a half an ounce. Figure out how to do that, to drop a few of the half-ounce sondes so that we can get profiles from the UAS. That's a little bit out in the future, but I think it's possible because of the weight.
Yeah, you probably heard of this. China, they use rocket.
Yes.
Those stuff.
Pete Black told me about that.
About 6.
I don't know where the rocket lands, but I guess that's not our problem. Frank has a question.
Okay, last question. We're a little over time.
So if we're going to do the evaluation of HAFs, we need to make the TC buoy database available to the community.
Sounds good.
So that we need to transition into the community so that people like Lou and the EOTT folks can make the analysis. And you should be a subject matter expert, obviously, but we need to get that database available.
Sounds good.
All right.
We went a little bit over. Thank you for joining, everybody. Appreciate it.
Thank you for the questions. This seminar will be available at the AOML website under seminars. Thank you again for joining. Bye.